Hey YouTube, thanks for visiting. Hope all you are live, doing well, and I think we are live now. Is anyone there? So please comment me once that the audio and video are okay or not. I think all the audio and video are okay. Okay. So if anyone is there, then please comment me once that the audio and video are okay or not, because I don't have any other screen to say or to see this live session. Okay. So just comment me once that the audio and video are okay. So this is the second session of West Bengal set 2023 question practice session, and in this session we are going to discuss the questions, or we are just practice the questions of linear algebra. Okay, so those who are watching this session for the first time, so I'll just introduce you that this is second session and we already take a first session on question practice session on real analysis for the upcoming West Bengal set 2023. Okay, so let's start, and before starting I am requesting you to all those who are new in my channel, please give a like to this video, share with your friends, and consider subscribing to my channel. Okay, chalo karte start. I think the audio and video are all okay, right? So if anyone is there, then obviously comment me once that the audio and video are okay. Okay, chalo bye. Karte start. Okay, so this is the West Bengal set exam upcoming target West Bengal set question practice series on linear algebra, and this is our WhatsApp group. So you can join the WhatsApp group for the question discussion or on West Bengal set or CSIR net or GATE exam. Okay, so let's start the session, and today's first question is this one. Okay, so I have total 20 questions in today's lecture. So if this session is going to lengthy, or the length of this video is going too far, then stop me over. Okay, so I'll stop. So the first question it says that let A be a matrix such that AQ equal to minus I, then which of the following numbers can be the eigenvalue of A? Okay, fine. So see, it is given that AQ is equal to minus of I. Okay, so that is the characteristic equation of this matrix A. This implies what? XQ equal to minus of 1. Okay, so XQ equal to minus 1. So see here, the matrix has that AQ equal to minus 1, but which field? Field is not given. Okay, so field is not given over R or over C, it is not given. Okay, so we here consider two cases, if this field is C and if the field is R. Now if the field is R, then the three roots of this equation are what? Minus 1, minus 1 and minus 1. Okay, and if this field is C, then XQ equal to minus 1, you all know that the roots are minus 1 omega and minus omega and minus of omega square. Okay, because since the roots of XQ equal to 1 is 1 omega and omega square, then the roots of XQ equal to minus 1 should be minus 1 minus omega square, where omega is given by minus 1 plus minus root 3 iota by 2. This is the value of omega. So that is the value of minus omega and omega and omega square value. Okay, so this is like omega is minus 1 plus root 3 iota by 2. So minus omega means this is equal to 1 minus root 3 iota by 2, and therefore minus of omega square means what? Minus of omega square means 1 plus root 3 iota over 2. I think I am writing okay. Minus 1 plus minus root 3. If we multiply by minus 1, then 1 minus plus. Okay, 1 minus plus root 3 over iota by 2. Okay, 1 minus plus. But minus 1. Okay. So anyone is there? I can see once. No. Okay, जो बाद में देखेगा कोई बात नहीं, ठीक है. So see, therefore matrix AQ equal to minus, which of the following numbers can be the eigenvalue of A? So the eigenvalue of A, iota, no. 1, no. It is minus 1, yes. If this field is R, then the eigenvalues are minus 1, and if this field is C, then C omega square, that is 1 plus root 3 iota by 2. This can be also one eigenvalue. Okay, so if the field is given, then obviously if this is R, then 1 is the answer, and if this is over C, So this can be the answer. Okay, this can be the answer. Okay, so if the field is R here we take, then -1, that is C is the correct answer of this problem. Okay, now next question. So it says that let A be an n by n matrix with AQ is equal to O, then we must have the only eigenvalue of A is 0, the only eigenvector of A is 0, A has n distinct eigenvalues. Option D, A has a real eigenvalues with multiplicity exactly 2. Okay, so AQ is equal to 0. That means clearly we all know that A is a nilpotent matrix, obviously. Nilpotent matrix of index 3 here. Okay, and we all know that all the eigenvalues of the nilpotent matrix are what? Eigenvalues of the nilpotent matrix are only 0, and here since the order of A is 3, therefore A has 3 eigenvalues, or n is the order of the matrix, so number of eigenvalues are n times 0. Okay, n times. So option A says that only eigenvalue of A is 0. Yes, option A is correct. Eigenvector of A is 0. No, eigenvector may never 0. Okay, A has n distinct eigenvalues. No, because it is nilpotent matrix. A has real eigenvalues with multiplicity exactly 2. It is not also correct, because the only eigenvalue is 0. Okay, and it is the multiplicity of n, because it is the order of the matrix is n. Okay, so this is the second question. And one more thing is that if the session is helpful for you, then obviously give a like and don't forget to give a comment in the comment section below. Okay, so the third question, the minimal polynomial of the matrix, this one. So the matrix is given that 3 3 0 3 3 0 and 0 0 6. See, sum of the row, each row, this is equal to 6, that is 6 is one eigenvalue, and the other eigenvalue, we all know that if this row sum is 6, then the eigenvalues is row sum 1 and remaining eigenvalues are 0, because determinant of this matrix is, sorry, this is 3, determinant of matrix is obviously 0. Okay, so now we have the 3 eigenvalues 6, 0 and 0. So here it says that option 1, x into x minus 1 into x minus 6, that is this 1 is an eigenvalue. No, the eigenvalue is only 6 and 0. Here 3 given, that is 3 is an eigenvalue, but 3 is not eigenvalue of this matrix. This is also false. X minus 3, x minus 3. No, 3 is present means 3 is an eigenvalue, but 3 is not an eigenvalue. The only eigenvalue is 0 and 6. So this is also incorrect. So that is the option D is the correct one. See, this is very easy problem. You don't need to go for मतलब 2 calculations की जरूरत नहीं है यहाँ पर, ठीक है. So the next question, the possible set of eigenvalues of a 4 by 4 skew symmetric orthogonal real matrix. So there are 3 terms: skew symmetric one term, orthogonal second term, and real matrix another term. So see, we all know that the eigenvalues of the skew symmetric matrix, real skew symmetric matrix, is either 0 or it should be purely imaginary. Okay, so 0 or purely imaginary is the eigenvalue of the matrix. Okay, and it is also given that this matrix is orthogonal, that is A transpose equal to 1, and we all know that A transpose equal to I, and we all know that the eigenvalues of the real or orthogonal matrix should be unit modulus, that is mod of lambda equal to obviously 1. Now here the eigenvalues are like 0 and purely imaginary. Now if 0 is an eigenvalue, then modulus of 0 equal to 0, it is not equal to 1. Therefore 0 is not an eigenvalue of the given matrix, that is the as per the given condition 0 may never the eigenvalue of the matrix. That is, we can discard the set that containing 0, so it discard. And so see, 0 and purely imaginary option only remaining here. So that is, this is real eigenvalue. No, it is not possible. It also contains real eigenvalue, so it is also not possible. Therefore the answer is clearly option A. Okay, now just see any comments or not. So audio and video are available, right? Anyone please comment me that audio and video are okay na? And please comment if anyone, if you have any questions or query, please comment, because I don't have any other displays to see your comments regularly. So comment me. Okay, so the next question, see, The next question is the dimension of the vector space B equal to Aij. Aij belongs to C, where Aij equal to minus Aji. That is, this is what? This is Aij equal to minus Aji means this is matrix with these types of matrix is called skew, not symmetric. It is skew Hermitian because the field is C here. Okay, so Q Hermitian matrix. Okay, this is also very easy question. So we all know the vector. If this matrix will symmetric, then we all know the formula for skew symmetric matrix. It will be n into n minus 1 by 2. Yes. Now because this is the field is of complex, so one complex number contains two real number. Okay, so this is the answer in the field C, that is the dimension of vector space if Aij equal to minus of Aji, that is if the matrix is skew symmetric, then the dimension of the matrix or dimension of the vector space is n into n minus 1 by 2. Okay, because there are two elements in each real number, therefore the dimension in case of complex field it should be like into twice. Okay, because A is a complex number means this is like A1 plus iota B1. So this is count in real number, but whether it is count in complex plane, then this is two real number. This contains two real number. That means the vector space dimension of the vector space C over R, this is equal to 2. Okay, that's why we multiply here 2. So that is this is equal to n into n minus 1, that is this is n square minus n. So option C is the answer. Okay, anyone doing any comment? No. So audio and video okay, right? Okay, chalo continue. Next question. If A is a 5 by 5 real symmetric matrix with trace equal to 15, okay, that is 5 by 5 means total how many eigenvalues? So summation lambda I equal to 1 to 5, and this is the trace of A equal to 15 given. Okay, fine. And if 2 and 3 are the eigenvalues of A with each algebraic multiplicity 2, that is 2 occurs 2 times, 3 occurs but 2 times. Okay, and one eigenvalue is remaining, and we all know that the sum of eigenvalues is equal to trace of the matrix. So if this is the lambda 5, then 2 plus 2 plus 3 plus 3, that is 6 and 10. 10 plus lambda 5, this is trace equal to 15. So that means lambda 5 equal to 5. Okay, therefore we have to find the determinant of the matrix. So determinant is product of eigenvalues. So det of A, this is equal to 2 into 2 into 3 into 3 into 5, that is the answer is 4 9 is 36 into 5 180. So option D is the answer. Okay, now next problem. Next problem is let A not equal to I. Okay, be an n by n matrix such that A square equal to A. Okay, no problem. A square equal to A where A is the identity matrix of order n. Which one of the following statement is false? A square equal to A, that is this means what types of matrix? The name of the matrix, like what? A square equal to A means involuntary. No, A square equal to Y. What? Oh, I find the name. So this is the matrix. Now if lambda is an eigenvalue, then it should satisfy lambda square equal to lambda. Okay, so that is we find the characteristic root, that is the eigenvalue of this matrix A. So lambda square minus lambda, this is equal to 0, that is lambda into lambda minus 1, this is equal to 0. This implies lambda equal to 0 comma 1. So we know the eigenvalues are 0 and 1, and these are the result. Okay, so if eigen C, the name is based on C, what? I just forget the name of this matrix. A square equal to A means the name of the matrix is what? A square equal to A means I forget the name. Oh, please comment me. A square equal to A means the matrix name. Just a second, I forget. So see, if A square equal to A, the matrix has the property that I minus A square equal to I minus A companion. No. A square equal to A means and trace equal to rank. It is also the property of the matrix, and rank of A plus rank of I minus A equal to n. This is the three property of the matrix, and you can easily discard the option which one of the option is false. So lambda is equal to 0 and 1, but here in option D it says that the eigenvalues of A are each equal to 1. No, because 0 is also an eigenvalue. Okay, so this is the answer. This is the false statement. Okay, you can easily verify. And these three are the result. Okay, these three are the result. Idempotent, sorry, idempotent matrix, idempotent. Okay, so this is the idempotent matrix. So if A is an idempotent matrix, then trace of A equal to rank of A. This is the result. If I minus A is also idempotent, that is I minus A whole square equal to I minus A. This is the result. And rank of A plus rank of I minus A is n. This is also result of the idempotent matrix. Okay, next question. A linear transformation T rotates its vector in R2 clockwise through 90 degree. Clockwise through 90 degree. The matrix T relative to the ordered basis is this 1 0 and 0 1. So which one of the following is the matrix? So this is also very easy problem. If you know the transformation matrix which called, so cos theta and sin theta minus sin theta and sorry cos theta I think minus sin theta and cos theta. This is the transformation matrix. Okay, so 1 0 and 0 1, that is this is compare करो इसको इसके साथ 1 0 and 0 1. Okay, so here you get simply theta equal to what? Theta equal to pi by theta equal to 0. Okay, theta equal to 0. If you compare this matrix with this, okay, so now it says that it is clockwise through 90 degree, that is in this direction. So we put theta equal to what? Minus of pi by 2 here to get our required matrix, because this is clockwise and we count or the angle is anti-clockwise is the positive direction for the angle case. Okay, so here you can just put cos of minus pi by 2, sine of minus pi by 2. Okay, cos of minus pi by 2, sine of minus pi by 2, and sorry I think this is minus sine and this is sine, cos sine minus sine cos. Okay, so this is minus of sine of minus pi by 2, sine of minus pi by 2, and cos of here minus of minus pi by 2, sorry minus of pi by 2 simply. Okay, so cos means this is cos minus pi by 2 or pi by 2, this is 0. Sine of minus pi by 2, minus of minus 1, that is 1. This is minus 1 and this is also 0. That is the matrix is 0 1 minus 1 and 0. Which option? Option B is the correct answer. Okay, so now the next question is, let T from Rn to Rn be a linear transformation, then which of the following statement implies T is bijective? You may say that the Sylvester's law is rank of T plus nullity of T equal to n, then in this case the rank is bijective, but no, this is not necessary, and which implies the condition implies. Okay, so this is not. So see, T is bijective means what? T is bijective means obviously it is injective. Okay, and injective means what? Nullity, obviously this is equal to 0. Okay, or dimension of nullity equal to, obviously you can say 0, or nullity is 0. Then rank is the complete rank, that is n. Now rank T minus nullity T equal to n. So rank n minus 0, this is equal to n. Okay, if this satisfies option D, option D is correct, not option C is correct. Okay, so nullity is n, it is false. Rank of T, this is equal to nullity of T, this is equal to no, this is also not correct. The correct answer is here option D. Okay, so it is which of the following condition? This is not implies that T is bijective. T is bijective implies this one, but this condition does not imply the bijective case. Okay, now the next question. So it says that for a fixed positive integer n greater or equal to 3, let A be an n by n matrix defined as A equal to I minus 1 by n into j. Okay, where I is an identity matrix with all the entries is equal to 1, with all the entries equal to 1. Okay, sorry, I think J is the matrix with all entries equal to 1. Then which of the following statement is not true? Okay, so if we take n equal to, suppose for a finite value 3, okay, that now a equal to what? A equal to, now the eigenvalue of a, so j equal to what? J equal to 1 1 1 1 1 1 1 1 1. So the eigenvalue of j is 3 0 0. Okay, and eigenvalue of I this is 1 1 and 1. Okay, now eigenvalue of a, what a equal to given? A equal to, it is given that I minus 1 by 3 j. Okay, that is eigenvalue of a, this is 1 1 1 minus 1/3 of 3 0 0. Okay, so this is 1 minus 1 0 1 1, that is the eigenvalue of a are 0 1 1. Okay, then it says that which of the following is not true? You can simply see from here that if eigenvalues of a are 0 1 1, then date is equal to obviously 0, because this is product of eigenvalues. Therefore option D says that a is invertible. No, this is the false statement, this is not true. Okay, you also verify that a to the power k equal to a. Suppose if we take choose k equal to 2, because this is for all positive integer a equal to 2, then the eigenvalues of a to the power square, that is a square, eigenvalues I can check through the eigenvalues. Okay, so eigenvalues of a square are obviously this same 0 1 square and 1 square, and this is same as eigenvalue of a, that is this is true statement. Okay, so this is true statement. And trace of a equal to n minus 1, obviously देखो trace of a is equal to what, यहाँ पर क्या है, trace is 0 plus 1 plus 1, that is 2, which is equal to same as 3 minus 1, n का value 3 लिया था. ठीक है, so this is also satisfied. So this is also true statement. And rank of a plus rank of I minus a, this is n. So you can also verify that I minus a. Okay, so I first find the eigenvalues of I minus a. So eigenvalues of I minus a, these are what? Eigenvalues of I are 1 1 1, and this is minus eigenvalues of a are 0 1 1. So 0 1 1. So this is equal to 1 and 0 and 0. So eigenvalues, so here only one non-zero eigenvalues, that is rank of I minus a, rank of I minus a, this is equal to 1. Okay, rank of I minus a equal to 1, and rank of a, here two non-zero eigenvalues. So rank of a, this is equal to 2. So rank of a plus rank of I minus a is equal to 3, which is equal to n. So this is also true statement. Okay, you can easily verify. So option D is false here. Okay, now the next problem, it says that let A be an n by n matrix with real entries. Which one of the following statement is correct? Okay, so a square equal to 0. Okay, and then a is diagonalizable. A square equal to which one of the following? A is diagonalizable. A square equal to 0 and A is matrix with real entries. Okay, this implies A is nilpotent. This implies non-zero nilpotent matrix. You all know that, not diagonalizable. Okay, so option A, it says that it is diagonalizable over complex numbers. No. So if A square equal to I, that is involuntary matrix, then A is diagonalizable over real number. And if A square equal to A, that is idempotent matrix, then it is diagonalizable over C. देखो, see, if A square equal to I or A square, this is equal to A, then this is involuntary matrix, this is involuntary matrix, and this is idempotent matrix. These both, okay, are diagonalizable over both R, the field is R and C. Okay, that is both in case of diagonalizable of idempotent matrix and involutory matrix, it is over the field both R and C. But here option C says that only over C. No, it's not. It is also diagonalizable over R. If A square equal to I, then A is diagonalizable over real number. Yes, because in here the term only is not present. Okay. And the only matrix of size n satisfying the characteristic polynomial of A is A. No, it's also not true. We can give you the examples. Okay, suppose A equal to 1 0 0 minus 1, then characteristic polynomial of A, this is equal to what? Lambda square minus 1, I think 1 minus lambda minus 1. Yes, and if we take B equal to minus 1 0 0 1, then characteristic polynomial of B is also same, lambda square minus 1. So see, it says that the only matrix of size n satisfying the characteristic polynomial for n equal to 2, here we take the 2 order matrix. So here characteristic of A equal to characteristic of B, but the matrix A is not same. Okay, so this option is also false. Okay, now the next question, the matrix minus 3 minus 1 0 minus 1 minus 2 minus 1 0 minus 1 3 is positive definite, non-negative definite. So here two process. One, to check positive definite or negative definite or indefinite, there are two processes. One is eigenvalue and second one is minor process. So here we apply the minor process, the principal minors. If the all principal minors are greater than 0, then this is positive definite, and the principal minors, suppose principal minors are what? First principal minor is this one, the second principal minor is this one, and the third principal minor is complete determinant of the matrix. Okay, now we calculate the principal minor. So the first principal minor, suppose A1, this is equal to 3, this is greater than 0. The second principal minor is this one, 3 minus 1 minus 1 2, the value is 6 minus 1, that is 5, which is also greater than 0. So A3 is the third principal minor. Okay, the third principal minor is the determinant of this matrix. 3 minus 1 0 minus 1 2 minus 1 and 0 minus 1 3. Okay, suppose we break this determinant, then the value is 3 into 6 minus 1 plus 1 into minus 3 and 0. So this is 3 into 6 minus 1, 3 into 5, 15 minus 3, this is 12, I think, which is also greater than 0. Therefore the three principal minors are greater than 0, that is the matrix is strictly positive definite. Okay, so if you all know that if the eigenvalues are strictly greater than 0, then this is positive definite, greater equal to 0 positive semi definite, less than 0 negative definite, less equal to 0 the eigenvalues are less equal to 0, then it is negative semi definite, and if the eigenvalues are greater than 0 and less than 0 mixed type, then this is indefinite. Okay, the quadratic form is indefinite. Okay, I think the answer is clear. एंड इन केस मैं एक बार जो नेगेटिव डेफिनेट का केस बोल देता हूँ कि यहाँ पर नेगेटिव डेफिनेट मीन्स A1 स्टार्टिंग इज लेस देन 0, देन A2 greater than 0, then A3 less than 0. If these types of situations occur in case of principal minors, then the matrix is negative definite. Next problem. Any comment? I'll just check once. No. Okay. Next question. Let A is equal to 3 1 2 1 2 3 and 2 3 1, and Qx is equal to x transpose x. This is a question from quadratic form. For x belongs to R3, then what? A has exactly two positive eigenvalues. All the eigenvalues of A are positive. Qx greater or equal to 0 for all x belongs to R3. Qx less than 0. So see, how can we check that all the eigenvalues are positive or negative? Okay, so check. First check. If we check this is positive definite, then we can say that the all eigenvalues are positive. Okay, so first find how can we check? Okay, one thing is that see here all the row sum are 6. Okay, 6. So 6 is an eigenvalue. Okay, now 6 is an eigenvalue that we can see from this matrix. Okay, fine. Now how can we say? Now we can find the determinant of A. Okay, so determinant of A we can find. So the determinant is 3 into 2 minus 9 minus 1 into what, 1 minus 6 and plus 2 into 3 minus 4. So this is minus 21 plus minus 5 plus 5 and minus 1 minus 2. Okay. So this is minus 18, which is less than 0. Okay, minus less than 0. See, this is a 3 by 3 matrix. Okay, fine. So the characteristic equation is obviously of order what? This is a characteristic equation is a polynomial of degree 3. Okay, these all are the shortcut tips. Okay, I don't go to the very deep calculation. So how can we observe that answers? Okay, so characteristic polynomial obviously degree 3. So if the characteristic polynomial of degree 3 and this is all real, because so x belongs to R3 means this is obviously on the field of reals. Okay, so we have a third degree equation, all roots are in real. So we can say that what this equation has since determinant is less than 0, then obviously one eigenvalue must less than 0, because we get one eigenvalue greater than 0. So lambda 2, suppose this is equal to 6, obviously greater than 0. So this is greater than 0. Therefore the remaining two eigenvalues, there is suppose lambda 1 and lambda 3, one must be greater than 0 and one must be less than 0. That's why from the determinant we can include the product of eigenvalues. 1 is greater than 0, we already get 6 is an eigenvalue. Therefore if the product of these three eigenvalues is negative, then you can observe that one eigenvalue must greater than 0 and second one is less than 0. Therefore we can conclude from here that A has exactly two positive eigenvalues. Option A is correct answer. All the eigenvalues of A are positive? No, it's not. And we get one eigenvalue or determinant is negative, that is this is the quadratic form is not greater or equal to 0. Okay, and this is less than 0 for all x. No, this is not for all x. For some of x this is true, but this is not true for all x. Okay, so that is, this is also not correct. Now next question. This is a very easy question. A positive semi-definite quadratic form fx x transpose ax, where x belongs to Rn and A is a n-row square matrix, is strictly convex, strictly concave, convex, concave. See, if fx, that is the quadratic form, x transpose ax, okay, if it is strictly greater than 0, then fx is positive definite, or you can say all the eigenvalues are greater than 0, then this is convex function. Okay, convex function. If it is positive semi-definite greater or equal to 0, then and it is strictly convex if greater or equal to 0. Okay, sorry, it is convex function if positive definite greater or equal to 0. If it all positive definite, then it is strictly concave, strictly convex, positive definite. Okay, strictly convex. And in case of negative definite, negative definite, it is strictly concave, strictly concave, and negative semi definite, this is only concave. Okay, so here it is given positive semi definite, that is greater or equal to 0 type. So greater or equal to 0 type means it is a convex function. Option C is correct. Okay, next question. Let A be a 5 by 5 matrix with real entries such that the sum of all entries in each row is equal to 1, then the sum of all the entries of AQ. So it is also very easy question if we consider one example. Okay, so if we take A equal to I5, then this is a 5 by 5 matrix and all the row sum, that is I5 is 1 0 0 0 0. So row sum is 1. Similarly second row 0 1 0 0 0, also 1 and so on. All the row sum is 1, you all know that. So it says that now if a equal to I5, then any integral power of aq, this is again I5, so that is same answer. Okay, so and here total 5 1 present and all the remaining element are 0. Okay, there it says that the sum of the all entries of aq, all entries of aq means this all, this is 0, this is all the entries, so that is this is 5. Option C is the correct answer. Okay, next question. So let A be an n by n matrix with the following which of the following equals to trace of a square b square. So here one cyclicity property you can use to find the trace of any matrix. So see, it says trace of a square b square. So a square b square means we can write a and b. Okay, so now we can write the cyclic like this way, a b and b. Okay, now if we start from here, then the trace of this order, cyclic order, all the matrices are same. So if we start from a, then we can write a b b, that is a b b, that is a square b square. Okay, now if we start from here, a b b a, that is a b square a. If we start from here, then b a, so b a, that is b square a square. And if we start from this point, then b a b, this is b a square and b. So trace of these 4 matrix, these and these are all same. So here only one given, a square b square. Now we see which option is given. Trace of ab whole square, no. Trace of a b square a, yes, this one is given, option B, so it is correct. Trace of a b whole square, no. A b whole square, no, this is not given. And b a, no, it is not given. So see, if this 4 option, if any of these 4 option is given in the answer or in the options, then this or the one or more than one answer should be correct. Okay, any comment? No. Next question. See, given the permutation sigma equal to this, a matrix A is defined to be one whose ith column of sigma I is the ith identity matrix I. Okay, of the identity matrix I. Which one of the following is correct? So see, this is a question from based on companion matrix. Okay, so no, not companion matrix. This is based on permutation matrix. And we all know that determinant of the matrix or determinant corresponding to the permutation matrix A is minus 1 to the power k, where k is the change, number of change in position to the identity matrix. That is, if the permutation matrix is given to number of change in rows or columns to form the identity matrix is this k. Okay, now how can we find this k? So this k is given by the order of the permutations. Okay, also called the order of the permutation. So order of the permutation, this is equal to number of cycles. So here it is given that the cycles, we can write this permutation in cyclic form. So 1, 3 and 2 is one cycle, and the second cycle is 4 and 5. Now order of sigma, how can we find? We can find LCM of the given are the cycles. Okay, so this is length 3 and this is length 2. So LCM of 3 and 2 is the order of the permutation, is equal to 6. So that is, we can write the order of the permutation a to the power 6. This is the identity matrix I5, I think, yeah, I5. Okay, so that is, we can get that a equal into a to the power 5 is equal to I5. So a equal to a to the power minus 5. Okay, this is the answer, option C. This is very easy question. Now next question. The trace of the matrix 2 1 0 2 0 2 0 0 0 3. We all know that if lambda is an eigenvalue of the matrix A, then lambda to the power n is the eigenvalue of a to the power n. So here the matrix A is given by 2 1 0 0 2 0 0 0 3. Eigenvalues of A, eigenvalues of A, what? This is upper triangular matrix, so that means the eigenvalues are the diagonal elements 2 2 and 3. Eigenvalues of A to the power 20 or lambda to the power 20, that is 2 to the power 20, 2 to the power 20 and 3 to the power 20. Now we have to find the trace. So trace of A to the power 20, this is equal to sum of the eigenvalues 2 to the power 20 plus 2 to the power 20 plus 3 to the power 20. This is equal to 2 into 2 to the power 20 plus 3 to the power 20. Option C is the correct one. Next question. Which of the following is not diagonalizable? Okay. So not diagonalizable. Fine. How can we find that whether it is diagonalizable or not? Not diagonalizable. See, if we see the matrix has distinct linear factor or the minimal polynomial is of distinct linear factor and the matrix has distinct eigenvalues, then we can see the matrix is obviously diagonalizable. So we can discard by using this result. See, if option we see this option, then since this is a lower upper triangular matrix, since the lower value is 0, so upper triangular matrix, so the eigenvalues are diagonal element 1 2 and 3. These are the eigenvalues and these are distinct. Okay, that means this is diagonalizable, but we have to find the not diagonalizable, so we can discard this one. Similarly, this 4 option also 1 2 and 3, and since this is also upper triangular matrix, so eigenvalues are 1 2 and 3, that is distinct, we can discard. This is diagonalizable. Okay, now in option 1 and 2, there are also the triangular matrix, that is this is also upper triangular matrix, this is also upper triangular matrix. Now the eigenvalues are 1 2 and 1 and the eigenvalues are 1 1 2. Two eigenvalues are same. So now we check the case AM equal to GM. Okay, if AM equal to GM for each eigenvalues, then this matrix is diagonalizable, otherwise not. Now if we check for option 1, so AM equal to GM, so we check, see this is 2 eigenvalues 1 times, that is AM equal to, so GM equal to again 2. So we find in case of the matrix eigenvalue 1, so A minus 1 into I, we first find rank of this. So this is A means 1 1 0 0 2 0 0 0 1 and minus of 1 0 0 0 1 0 0 0 1. Okay, this is equal to 1 minus 1 0 1 0 0 1 0 and 0 0 0. So see, rank of this A minus lambda I or 1i, this is equal to 1. Therefore nullity, that is the geometric multiplicity, equal to 3 minus this one, rank of this is 1, so this is 2. So this is GM and AM equal to also 2, so that means this is diagonalizable. So this option is not correct. Therefore which one of the following is not diagonalizable? Only one option, option C. Also you can check by using the AM or GM. Okay, for in the eigenvalue here 1. Now next question. So if A equal to this matrix, this is again a lower triangular matrix, the upper values are 0. So trace of A to the power 102. So see, the eigenvalues are what? These element, diagonal elements, eigenvalues. So eigenvalues are 1 minus 1 plus iota root 3 by 2 minus 1 minus iota root 3 by 2, that is, this is, we all know that, well known from 1 omega omega square. Okay, now if these are the eigenvalues, therefore eigenvalues of A to the power 102 are lambda to the power 102, that is 1 to the power 102 omega to the power 102 omega square to the power 102, that is 1 omega to the power 102 means we all know that omega cube, this is equal to 1. So we can write omega to the power 99, yes, this is omega cube to the power 34 and this is omega to the power 202 and 202 means 102 we can divide 202 by 3, that is what, this is equal to, you can write omega cube to the power no, it's I think 70 202 3 2 67 omega to the power 67 and into omega. Okay, omega to the power 67 into omega. So this is 1 omega cube means 1 to the power 34, and this is again 1 to the power 67 into omega, that is sorry I think this is 202 omega to the power 102 omega square to the power, oh sorry, this is 204, right? So 204, and 204 means I think it's omega to the power 68, not omega to the power 68, 1 to the power 68, omega to the power 3 to the power 68. So this is 1 1 and 1, that is trace of a power 102. This is 1 plus 1 plus 1, this is equal to 3. Okay, so option D is the correct answer. So these are the total 20 questions from linear algebra for practice questions for WBSET 2023. Okay, so this is the second lecture, and we already take the first lecture on real analysis. This is first lecture, and you will get the description. In the description you will get the link, and you can also check the iTap, or you can also go for WBSET mathematical science playlist. This is the playlist. Okay, WBSET mathematical science, WBSET mathematical science. You can go this to this playlist, and you will get the previous videos. Also you can get the pyqs already solved in the channel for WBSET. Okay, so if this series or if this lecture is helpful for you, then obviously give a like to this video, because to make one video, it is very hard work behind this class. Okay, so thank you, and if this you like, if you need these types of more videos, so you can definitely comment me in the comment section, and I can expect one comment from you, obviously. Okay, so each of everyone, those who are watching this channel or watching these lectures, so you can please comment me. One comment is more than enough. Okay, so thank you, bye. I find today's lecture is end here. Okay.